So I'm just going to draw an alkene here and talk about this a little bit. So alkenes, they have pi bonds. Because of that, they are nucleophiles of Lewis bases. So the reactions we study in class for alkenes were reactions with electrophiles. Electrophiles that we learn in class for alkenes were basically, for example, the hydrogen ion. That was one electrophile. For acid catalyzed hydration, we know the hydrogen ion is a good electrophile because obviously we got hydrogens that are bonded to highly electronegative oxygen. And in addition to that, the oxygen is positively charged, which is not good. So it's dying to lose a proton to go back to water. We're missing a lone pair here. So hydronium is a classic example of an electrophile used for electrophilic addition reactions over alkenes. We also learn borane. Boron is a very good electrophile because again, boron is on the second row of the periodic table. It has 4 orbitals in its valence shell. So it achieves stability with 8 electrons. It has 6, so it's dying to receive 2. Hybridization of boron is sp2. It has an empty p orbital. So it's really looking forward to accept 2 electrons to complete 8 electrons in the valence shell. So another very strong electrophile we studied in class was uh, um, mercury sulfate in acid media. We know mercury acetate, sorry, my apologies. So mercury sulfate is also an electrophile, but we use it for, so mercury acetate. So once again, mercury bonded to oxygen, which is highly electronegative. So that makes the mercury to be highly electrophilic. Another reagent we learned in class was bromine. We know that bromine adds to double bonds very quickly. Remember I said this bond in between the 2 bromines is weak, the sigma bond, because of the repulsion of the lone pairs of each bromine atom. We know now addition of bromine to double bond is a classic reaction, bromonium bridge formation. So that was another, this is not helping anyways. So that was another reaction we studied in class. And then, so we also studied the addition of bromine with nucleophilic solvents, like for example, water to form halohydrins. Don't remember if I might be missing one, but we can start talking. So we also study about reduction and oxidation reactions. For example, oxidation with osmium tetroxide. We study also oxidation with ozonolysis reaction, which breaks the double bonds that form carbonate compounds. And we also study reductions with hydrogen. So catalytic hydrogenation reactions. Okay, so if we talk about these reactions quickly, let's say, so acid catalyzed hydration is simple. Once again, that's a reaction of, for example, hydrobromic acid. So acid catalyzed hydration. I'm sorry, we also discussed here, that's the one I was missing, my apologies. Hydrogen halides. So we know hydrogen halides are classic electrophiles because of the bond polarity here, and also bromine being a great leaving group. So addition of hydrobromic acid to an alkene, step 1, formation of a carbocation. We know that only the most stable carbocation is formed. So in this case, a carbocation will be formed at this position here. I'm not going to do the mechanism in details because that will take a long time, but this is in the textbook. We discussed this in class. So carbocation form at this position over here, and in the step 2, the nucleophile attacking the carbocation. So that will lead to a bromoalkane, once again, the highest substitution of the double bond. So it's regioselective because once again, only the most stable carbocation is formed. Step 1, formation of a carbocation. Step 2, nucleophilic attack of the bromide over the carbocation, okay? In this case, the resulting compound is not chiral, so I don't have to worry about stereochemistry. If you happen to create a chiral center, you'll get a racemic mixture because once again, carbocations are trigonal planar, okay? So, that's for hydrogen halides electrophilic addition. The same mechanism applies to acid catalyzed hydration. Once again, in this example that I'm giving you guys, a carbocation is formed. There is no option of rearrangement. So, but I'm gonna say here in general terms for electrophilic addition reaction. So we got step 1 is formation of a carbocation. And the moment we have a carbocation, you have to ask, could potentially this carbocation, could it be able to rearrange? Okay, and step 2, nucleophilic attack. Of course, there are examples like butane and then oxymercuriation in which there is no free carbocation, but still you're forming an electrophile, okay? So for hydrogen halides and acid catalyzed hydration, it's the same mechanism. Both reactions go through step 1, formation of a free carbocation. If that carbocation can rearrange, it will to form a more stable carbocation. If it cannot rearrange, as it is the case that I'm showing here on the board, then the second step will be just the electrophile attacking the carbocation to form the final product, in this case, an alcohol after deprotonation. So acid catalyzed hydration allows us to form an alcohol from an alkene regioselectively. Once again, the alcohol ends in the highest substituted carbon always, because that's where the carbocation is formed. So, hydroboration oxidation, I just explained why butane is a good electrophile. Boron, very, very electrophilic. So remember, it's a two-step reaction. Step 1, butane. Step 2, oxidation. So in step 1 with butane, we are forming a trialkyl butane. And then in step 2, we are oxidizing the trialkyl butane to an alcohol. Important thing, butane binds to the lowest substituted carbon always, right? So butane, that means that the hydroxyl group of the alcohol is going to end up always in the lowest substituted carbon. Very important to keep that in mind. I'll give you 1 second. Okay. Somebody has asked a question. Let me see. So for acid catalyzed hydration, if there is a secondary carbon next to a tertiary carbon, even if the tertiary carbon is not part of the pi bond, the OH will go to. So in that case, if Milena, in that case, what might be happening is a rearranged carbocation. So once again, for acid catalyzed hydration and hydrogen halides in these two examples, if the carbocation can rearrange, it will. Okay. So going back to, you have to know if there are enantiomers, of course. In this case, the final molecule is not chiral, but if it is chiral, you get a mix of enantiomers and you need to reflect that. Stereochemistry is very important. So in this specific example, once again, hydroboration, boron binds to the lowest substituted carbon. So that's where the hydroxyl is going to end up. And the hydrogen and boron are adding with syn stereochemistry. So they are added to the same phase of the double bond. So we need to keep stereochemistry in mind. So that means that in a case like this, we get 2 enantiomers, 1 enantiomer in which looking like this, in which the hydrogen and the boron are on the bottom face, on the top face, and the second enantiomer in which the boron approach the double bond from the opposite face, and in that case, we get opposite stereochemistry. You have to draw the proton because we need to show that this is syn addition in this case. okay? So I'm indicating that the hydrogen and the hydroxyl are on the same phase here and on the same phase here, both enantiomers. So the reaction is regioselective because the hydroxyl ends in the lowest substituted carbon. The reaction is syn stereoselective because the hydroxyl and the hydrogens are adding in the same phase of the double bond. Not
Professor, so when you're adding, I apologize, but when you're adding the BH2, it's on the same face as the hydrogen, correct? So when you add the OH, there's no type of inversion, it remains on the same face?
it remains in the same phase. So the stereochemistry is not lost in the oxidation.
Okay, understood. Thank you.
So so remember once again, no rearrangements in hydroboration because there is no free carbocation. Okay. Boron binds to the lowest substituted carbon because of aesthetic effects. That's why the triacylborane is happening here. Okay. So guys, ask you where if you have questions about the reactions that I'm presenting, just type them on the chat and I will address them. We also study, as I said, oxymercuriation reduction. So we were using mercury acetate in step 1. Formation of a mercurinium bridge, remember, is what's happening here. The mercurinium bridge, you have 2 electrons shared between 3 atoms. The mercurinium bridge can form on both faces, top and bottom face of the alkene, so you get 2 mercurinium bridges always. Keep that in mind. The alkenes are trigonoplanar, so those double bonds are flat. So every electrophile, guys, remember, can always approach the electrophile from above and from below the plane. Okay, so oxymercuriation is a mercurinium bridge. Mercurinium bridge means that basically you got, and I'm gonna briefly draw the structure here just to make sure you guys remember. So you got 2 mercurinium bridges being formed. Oops, I'm sorry. It's not allowing me to do this. I don't know why. Let me see. So it's more or less this, okay, with the mercury acetate right here. I'm gonna show stereochemistry here so you can see that the mercurinium bridge can form below the plane of the molecule and above the plane of the molecule. So I'm trying to remove that. Okay, so you get this mercurinium bridge and you also get the other one. So meaning that above the plane. And then in step 2, the nucleophile, which is water in this case, is attacking the electrophilic center at the highest substituted carbon only. So the attack of the nucleophile, once again, the nucleophile is water, is the solvent, and water is attacking regioselectively only the highest substituted carbon because that's the carbon with the highest partial positive charge. That leads to, obviously, to an alcohol as a final product. In this case, the final product is achiral, so it's not a problem. But if you happen to create a chiral center, you will get 2 enantiomers because you get 2 mercurinium bridges. So keep that in mind. That's why I did this on purpose here, so you can see the mechanism. No rearrangements also in oxymercuriation reduction because you got a mercurinium bridge. So same as in hydroboration. So guys, hydroboration, oxymercuriation, and acid catalyzed hydration are 3 methods to transform alkenes into an alcohols. The big difference in them is in acid catalyzed hydration, you do get rearrangements, not in these two, hydroboration or oxymercuriation. Hydroboration is opposite regioselectivity, so the alcohol is in the lower substituted carbon. Oxymercuration is opposite to that. Okay.
So Professor, for oxomercuration, we don't have to show the products as anti, only the.
Yeah, no, because in the reduction, that stereochemistry is partially lost, so that's why I never mentioned that.
Oh, okay. So we just have to show the products, the end one, and that's it. The
Yeah,
last.
if in the first step, the oxymercuriation, because of a mercurinium bridge, after step one, you do get anti the 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 hydroxyl and the mercury acetate are anti-coplanar, but in the reduction, that stereochemistry is lost. So in the overall result of the reaction, we never draw the anti-coplanar because of that.
Oh, okay, got it. Thank you.
So bromination reaction is a classic electrophilic addition reaction. We got a bromonium bridge is a reaction intermediate, so we know that. Once again, the bromonium bridge is formed on both sides of the alkene. So we got one bromonium bridge from the top. And one bromonium bridge from the bottom. I'll draw both of you so you see. As I said, guys, this is when you're practicing the reactions and all these things, important is to keep the mechanism and the details of the mechanism in mind. So we got the bromonium bridge from the top face here. Remember, we have a methyl group. So let's show the methyl groups on the opposite face here. And we got the opposite bromonium bridge. In that case, opposite stereochemistry. So two bromonium bridges, and that leads to step number two is a nucleophilic attack of the bromide on both carbons of the bromonium bridge. So we discussed that in class. So that leads to the final products in which we get two bromines ending up transdiaxial in this case, or anti-coplanar whenever you got a linear alkene. So in the case like this, we'll end up with a bromine on this side. Anti-coplanar will have another bromine here. And then we got obviously the methyl group here as well. And the enantiomer of this, because remember both carbons are receiving the nucleophilic attack. So we gotta keep stereochemistry in mind. So both bromines, once again, anti-coplanar. So bromination reaction, classic electrophilic addition reaction, it creates two bromines. Once again, they end up anti-coplanar or transdiaxial. Two enantiomers are formed because you got two bromonium bridges here. The reaction is anti-stereoselective precisely because both bromines are ending anti-coplanar. What else? The reaction is stereospecific. Remember, we talk about cis alkenes giving different products as trans alkenes in bromination reactions. So that's an example of an stereospecific reaction. Stereospecific reaction, the stereochemistry of the products depends on the stereochemistry of the reactants. So that's what you need to know for bromination. So we can also do bromination with, instead of using a solvent like dichloromethane or anything that is non-reactive, you can also do bromination in water. And in that case, because water is a Lewis base and you're using water as a solvent in step two, after the bromonium bridge, now the water molecule will be attacking the bromonium bridge regioselectively, right? So we got the same, exactly the same intermediates for the halohydrin formation. And then what happens here is now the nucleophile, once again, water, will be attacking regioselectively the highest substituted carbon, which is this one here on both bromonium bridges. So water, that's a carbon with the highest fraction of positive charge. So the most electrophilic carbon is this one. So in step one, formation of a bromonium bridge, step two, water, the nucleophile is attacking the highest substituted carbon. So that leads to, once again, halohydrins, regioselective products in one case. So obviously the hydroxyl is always going to be bonded to the highest substituted carbon, and it's going to be anti to the bromine. So that's a product for these two. Okay. So we got two products once again because two enantiomers are formed. Um, the nucleophile here is once again water. Because you're using water as a solvent, you have billions of molecules of water versus bromide ions. So that's what's happening.
So, sorry,
the,
Professor. Just to
Mhm.
be like clear, so OH is always gonna be on the most substituted, and then bromine's always gonna be on the least substituted, right? In terms of
Yes,
the product.
because the OH is coming from the water that is attacking in step two only the highest substituted carbon.
Okay, thank you.
And then you got the protonation after that, of course, right? So two things, the regiochemistry, the hydroxyl in the highest substituted carbon, stereochemistry, the hydroxyl and the bromine are anti-coplanar or transaxial. Keep that in mind. Okay. So in another example of reaction that we learned here that I discussed was the osmium tetroxide oxidation. As I said before, well, osmium tetroxide is just adding a cis diol. Let me see if I can write it here. It's forming an osmiate. You can see I'm not going to draw the intermediate of the reaction. You can find in the textbook pretty easily. So once again, we are adding two hydroxyl. It's a cis addition because both hydroxyls are coming from the same molecule, the osmium tetroxide. Let me write the reagents here. And we usually do these reactions in the presence of peroxides. So it's a catalytic amount of peroxides. To regenerate the osmium tetroxide. So it's an oxidation. So remember in organic chemistry, oxidation is adding oxygens, reduction is adding hydrogens, right? So we add two hydroxyls in the same phase of the alkene. So it's regioselective. And of course, the osmium tetroxide can approach the alkene from both the top and the bottom phase. So you get, once again, two enantiomers because the alkene is trigonoplanar. So you can reach the alkene from both faces. So you got two enantiomers, turn them here. So it's a cis oxidation, cis diols. So two alcohol functional groups, that's what we call a diol, and both are ending on the same phase of the alkene. Okay, so that's osmium tetroxide. We talk about also ozonolysis. Ozonolysis is so you need to use so it's a way of breaking a double bond to make a carbonyl compound. So you can, so if you got, so you're breaking a double bond here to make a carbonyl. If you have a, sorry, a tetra substituted alkene, like in this case, so you got two substituents here. So once you break, you're gonna get a ketone. Here, you're gonna get an aldehyde because there is only one substituent. Okay, so we got 7 carbons. We get 2 ketones. I'm not expecting you guys to know the mechanism for photosynthesis, so you don't need to worry about that. And hydrogenation is just reducing this to an alkane. So remember, we need to use a catalyst for that. Could be palladium, could be nickel, could be platinum. Let's say palladium, and that just reduces the alkene to an alkane. It's also state specific because it's a cis reduction. In this case, it doesn't apply once again because we're not getting anything chiral, but the both hydrogens are adding on the same face of the alkene. Okay. So